All right, guys, so we're going to talk about function continuity and discontinuity here. In general, we're going to say functions are continuous on intervals of the x-axis where the ordered pairs connect, and we have points of discontinuity on the x-axis where the ordered pairs do not connect. And in general, what we want to see here is that both continuity and discontinuity are defined on the x-axis. The first type of discontinuity we're going to look at is infinite discontinuity, and we're going to say that we have infinite discontinuity where we have a vertical asymptote. So right here, for our first function, 1 over x minus 2, we can say that we have a vertical asymptote at the x value of 2. And if we take a look at the graph of the function, we can see a very clear break in the ordered pairs, right? Where at x equals 2, we do not have ordered pairs connected. When we call this infinite discontinuity, really what we're doing is describing what's happening with the function value. So because as we approach x equals 2 from the right, our function values go up to positive infinity, and as we approach from the left, our function values go down to negative infinity. The function values don't ever end, and so basically we can say that there is an infinite discontinuity there. Now we would just write this as infinite discontinuity at x equals 2. In general, we're going to say that infinite discontinuity is non-removable. And the reason we're going to say that is because there's no way we can redefine the function at the x value of 2 to connect the two pieces here, right? There's always going to be function values going up to positive infinity and down to negative infinity as the x values get closer and closer to 2, so there's no way we can connect those two pieces. The next type of discontinuity we're going to talk about is removable discontinuity. And with removable discontinuity, basically what we're seeing is ordered pairs not connecting due to one missing ordered pair. So if we take a look at our graph right here, we can see that at the x value of 2, we're missing one ordered pair that would let the ordered pairs of our function connect. So right here, we would say that we have removable discontinuity at the x value of 2. In general, we say that we have removable discontinuity when the factor that is giving us 0 in the denominator is also a factor of the numerator. So right here, if we look at our g of x, we've got x squared minus 2x divided by x minus 2. And if we factor out the numerator, we would have x times x minus 2 divided by x minus 2. So we can see that x minus 2 is a factor of the numerator and denominator. Now right here, when x equals 2, we are dividing by 0, and so we're undefined. But for all other x values, we have the x minus 2 in the numerator giving us the same number as the x minus 2 in the denominator, which means that we would be multiplying and dividing by basically the same number. So we would see our x minus 2's cancel out, and we would get the graph of the linear function x for all x values except for the x value of 2. So this gives us removable discontinuity at x equals 2. And again, we're calling this removable discontinuity because if we could redefine our function at 2 to be 2, we would have the ordered pair that would fill in our discontinuity. Now, we can't do that. The function is defined with the equation that we're seeing right here, which gives us that removable discontinuity. But theoretically, if we could redefine the function to give us just one ordered pair, the ordered pair 2, 2, we would have a continuous function at the x value of 2. So it's removable discontinuity. Okay, so the last type of discontinuity we're going to look at is really something we see a lot more commonly in piecewise functions, which we'll look at in the next section. We're going to say that jump discontinuity happens where we have a jump in function values, right? So basically right here we're seeing our function values go from -1 to +1 at x equals 0. Now right here, we've got a very special case with our h of x, where we've got the absolute value of x divided by x. And here we can see that as we plug in negative x values, we get positive numbers divided by their corresponding negative numbers, giving us -1 all the way up into 0, where we're undefined because we have 0 in the denominator. And then right here, when we start dividing by positive numbers, we've got positive numbers in the numerator divided by their corresponding positive numbers. So right here, that gives us +1 for all positive x values. And here we would say that we have jump discontinuity at x equals 0. Now right here, this would also be removable discontinuity, or I'm sorry, non-removable. Because there's no way we can redefine the function at 0 to connect our two pieces, right? Again, this is something we're going to see a lot more in the next section. We're mostly going to be looking at infinite discontinuity and removable discontinuity here. Now, for this last function, f of x equals x squared plus 2x minus 1, we're seeing a function that is continuous everywhere on the x-axis. Just looking at the equation that defines this function, we can say that there's no variable expression in the denominator, an expression with x in the denominator that could potentially give us a vertical asymptote or removable discontinuity or even jump discontinuity like we're seeing right here. And if we think about the graph of this function, with the square, we've basically got a parabola that opens up, and we know that for parabola, we're seeing our function values come down to the vertex and then go back up to positive infinity, and we can anticipate basically no breaks in the ordered pairs of this function, right? So we would say this function is continuous everywhere. Now, we know that the domain of this function is -infinity to positive infinity. We're defined everywhere on the x-axis because we have no domain restrictions that we're violating here. We're also saying that we're continuous from -infinity to positive infinity. And in general, if we're continuous on the entire domain, we can just state that. We can say continuous on domain, which we can abbreviate with just D. Now, if we look at our example of jump discontinuity, we would say that we have a domain from -infinity to 0, union with 0 to positive infinity. And similarly right here, I'm just going to erase this so we can see it a little better, the only break we have is at the x value of 0, where we don't have a function value, right? X equals 0 is not in our domain. So similarly right here, because the only break we have, or the only point of discontinuity we have, is at an x value where the function doesn't exist, we can say that this function is also continuous on domain. Looking at our removable discontinuity, just looking at the equation here, we can say that the domain for this function would be -infinity to 2, union with 2 to positive infinity. And similarly right here, we can say this function has connecting ordered pairs everywhere but the single place where it doesn't exist. So we can say this function is also continuous on its domain. And finally, with our vertical asymptote, we have a function that has domain from -infinity to 2, union with 2 to positive infinity, where the only point of discontinuity is a point that's not on its domain. So here again, we could say we are continuous on domain. Okay. Now, just because all of these functions are continuous on their domain doesn't mean that every function is continuous on its domain. We will see some examples of piecewise functions that are specifically not continuous on their domain, but it is possible for a function to have a point of discontinuity and still be continuous everywhere it exists on the x-axis. Okay, so we've looked at continuity and discontinuity. I'm going to give you guys some problems to try. I want you guys to go ahead and see if you can find the domain and identify any points of discontinuity for these two functions. And pause the video here, and we will come back and take a look at this in a second. All right, guys, so looking at this first one, we've got y equals 5x plus x to the -2. Now that x to the negative 2 can be rewritten as 1 over x squared, where we can clearly see x equals 0 is the x value that will give us 0 in the denominator. So right here we exclude 0 from the domain of our function. We can say that our domain is going to be negative infinity to 0, union with 0 to positive infinity. We're going to say that x equals 0 is going to be a vertical asymptote, which means that we have infinite discontinuity at x equals 0. Now, it might not be so easy to see this, but one thing we can do is create one fraction equation here. Right here I can take my 5x and write that as 5x cubed over x squared plus 1 over x squared. And then right here I can see that when I combine, I've got 5x cubed plus 1 divided by x squared, where x is not a factor of both terms in the numerator. So we know that this is going to be infinite discontinuity at x equals 0. So for our f of x, right here we've got x over our x squared minus 3x. And if we factor the denominator, we can say that we've got x times x minus 3 in the denominator. Now right here we've got x equals 0 and x equals 3 as both being zeros of the denominator. So our domain is going to be negative infinity to 0, union with 0 to 3, union with 3 to positive infinity. Right here, the factor that gives us 0 as a 0 of the denominator, just x, is also a factor of the numerator. So we can say that that's going to be removable discontinuity at x equals 0. The 0 we get from our x minus 3 is, of course, 3. So we will see a vertical asymptote at x equals 3, which is, of course, infinite discontinuity. All right, guys, so that's all for this video. And we'll try some of this tomorrow in class.